Welcome to The Mixer. This is Andy Marshall, your MC. I'm here with my friend Juan Carlos Lopez. How are you doing, JC?
I'm doing very well, Andy. Very happy to be here and to be back in The Mixer. It's been a while since we have sat together to have what hopefully will be an interesting conversation. So who is our guest today?
So today we're talking to Sebastian Giwa. Seb, I first came across nearly a decade ago when he was setting up the Organ Preservation Alliance, which has now led to the formation of an research institute called the Biostasis Research Institute. Seb's interesting because he's really a thought leader, and I would say more than that, a lightning rod in bringing together a diverse set of people, whether they're cryobiologists, bioengineers, or transplant surgeons, to create what I think is a kind of new field seeking to modernize organ preservation, and by doing so, change some of the dynamics and the availability of organs for organ transplantation.
Yeah, this is very interesting. It's an unmet need in biomedicine. A lot of people die waiting for an organ. So anything we can do to increase the number of organs and get more of them to patients is certainly a welcome idea. So I look forward to this conversation.
Yeah, it's really sobering, actually. The demand for donor organs outstrips the supply by a factor of 5 to 1. So in the United States alone, I think there are over 120,000 people on the transplant waiting lists, and obviously many more than that worldwide. So this is a really, really important problem.
Let's get started then.
Yeah, let's join the conversation. So Seb, welcome to The Mixer. It's great to have you on the show.
Yeah, it's honored to be here.
We've been eager to chat with you because of, in my view, you have played a unique role in galvanizing efforts around organ preservation research, bringing together the clinicians in transplantation together with researchers as well to build this community that didn't exist before. Perhaps by way of introduction, you could lay out some of the background about how you came to see this problem, organ preservation.
Absolutely. So back about a decade ago, I had that opportunity to go out and live on the NASA campus, Mountain View in Silicon Valley, Moffett Field. And it was a 3-month program called the Global Solutions Program, where young leaders from all types of interdisciplinary backgrounds were brought together with the mission of find something where a small team of us could go out and positively impact 1 billion people. And very different than all of these other company accelerators and so on, where instead of it being we'll help you work on the problem, it was much more we'll help you systematically think about what problem should you actually select? Like what grand challenge is the right one to pick? So 90% of those 3 months living on the NASA base, we were basically constantly spending thinking about, okay, what does the world look like today? What could it look like in a decade if we nudged it in the right way? What could we be the catalyst to kind of, change the course of human history? I actually joined thinking I was going to work on poverty and education, and my dad is from Ghana, and ended up just meeting some amazing scientists and physicians who joined the health team. And we had 200 different post-it notes in our office, let's go cure cancer, like all of these things. And I think at the end of the day, what really was so powerful with the intersection of organ transplantation and basically biostasis, or stopping or controlling biological time. It wasn't just something that would be truly transformational from an impact perspective, but it felt like it was a field that was orphaned and neglected. Mm-hmm. At the same time that there were so many converging areas of science and technology around it that were creating a platform that the time was now. Like it would work today. Maybe it wouldn't work 3 decades ago, but today we could really achieve those game-changing type of results. So that was the process. It was, quite systematic. And in hindsight, it ended up going so much better than we ever thought, when we were taking those walks in the middle of the night, dreaming of these concepts back on the NASA base.
So obviously you had conceptualized the problem, identified what could be a potential solution, and then you had to kind of think about, well, how are we going to tackle this? Tell me a little bit about how you thought about the problem and how to tackle it.
So a big part of the training, at Singularity University, Peter Diamandis, Ray Kurzweil, among maybe our generation's best people about thinking outside of the box, we felt it was really important that we did a lot of thinking from first principles and not just looking at what the field said. But at the same time, we understood that there were, so many people that for decades had been thinking about at least related areas. So there was this tension of, when we did the first round of basically meeting and interviewing with all of the top scientists in these related areas, almost everyone was, you're never going to stop time entirely at cryogenic temperature for a whole organ. That was basically the belief. There were some outliers that thought it would be possible if you had resources, but they didn't think the resources would be there.
And even the people in cryobiology thought that, yeah?
Yeah, exactly. There's a paper in PNAS where they interview Gloria Elliott, who's Canada Thermodynamics chair, and she basically says, I did not think it was possible. And this is, 5 years in. And then she says, but my opinion has changed. So we could kind of see how that shifted. But to the underlying question there, Andy, I think it was the combination of us really thinking about, okay, but what if we brought in some of this other technology or this other, scientific field that eventually when we did the road mapping together with the scientists in the field, we laid out a path where now everyone really thinks it's relatively near term. And some of the technologies, we don't have to go all the way down to stop time, but we just control it. And instead of, having hours, we won't get indefinite, but we can still get maybe days or a week or so. That might be in the clinic, already in 18 months or so, the first examples.
So you undertook this exercise, you talked to all of the KOLs in the field, and then you understood that, so we need to create a kind of focus, yeah? Like some organization that's going to focus all of these activities. This is where I first became aware of you. You were working with Jed at the Organ Preservation Alliance.
Yeah.
So tell us a little bit about what the Organ Preservation Alliance is.
It's kind of like a mini American Cancer Society for this specific goal of what can we do to stop biological time? So for any, complex tissue or organ system, how can we put it in stasis through low temperature biology? We basically brought the world together at scientific summits. So we had one at Stanford first, another one, Harvard Medical School. We went out to West Point and did one with, the Defense Department that we brought a lot of the top scientists from all around the world. The National Science Foundation came in with some grant funding where we were able to do this in-depth road mapping of both what are all of the remaining sub-problems and then what's the convergent science that you can go after to solve those remaining sub-problems, but also to really break down what are all of the areas of biomedicine, because the more we looked at it, the more we realized that it's not just organ transplantation per se, but there's so many other areas of medicine that would benefit. And after having built that consensus and that engagement, the Defense Department, we kind of lobbied them. They were the quickest to come out with, these targeted grant funds. And that led both to all of the teams that ended up getting funding, but also a lot of other labs that didn't get funding were still trying to get the funding, so they were thinking about the problem. And then they got, other types of funding from the NIH and so on. And then we basically saw this explosion of activity around these different labs. And then the final stage of my involvement with Organ Preservation Alliance was that Jed Lewis, who took over as CEO, basically had this call where it went out to thousands of people that had at any point done anything in cryopreservation, asking who would want to lead a large-scale effort if we help you put that together. And it turned out that the two top proposals came from the MGH team in Boston and then the Institute of Engineering and Medicine that's at University of Minnesota. And we knew that they knew each other. So Jed asked them if they would work together instead of being like finalists that would only, one would get the support. That became basically the Biostasis Research Institute. And then out of that, those two labs, with some support from Organ Preservation Alliance, went after the National Science Foundation, their top kind of grand challenge type of center support that they can have for engineering research center. So ATB Bio now, has been up and running for about 3 years, which supports more than 30 different PIs across the country, 6 institutions. That is maybe 10 times faster, the scientific advances are happening now than they were before.
And this is really important, Sabia, because cryobiology was this really far out field. It wasn't a field that was front and center in biomedicine. Maybe people would challenge me on that, but to me, that's the difference between you and Jed coming into this field, creating the Organ Preservation Alliance, really galvanizing all of the key figures, bringing in people in the clinical community who are thinking about these problems. It became a really different proposition from what it was before that. And you had really placed the possibilities in front of the research community and said that we are ready. Go ahead. Is that a reasonable summary of how you would see it?
Yeah. I think there were kind of silos where you had seen the transformational power of cryopreservation in the past, right? So how it enabled the whole fertility world of IVF and people can preserve, eggs and sperm and embryos. That was one example of that. And similar how those tools have been used in many ways to transform agriculture. But I think what you said is a good description of how it ended up being for these larger complex systems, like a whole ovary to, protect the fertility of a young pre-puberty cancer survivor, or the organs for transplantation. There, I think what you said is a very good synthesis.
Getting a little into the biology of this, cryopreservation, not of organs, but of cells, has been possible for a long time, right? And embryos and these sort of things. So, number one, what was the main roadblock to go from where we were and being successful with individual cells and with embryos to get it to work in actual organs? Is it the perfusion? Is it the surface to volume ratio? Is it something completely unexpected? So what was the roadblock?
A lot of it has to do with surface to volume ratio and, how heat transfer works, where you can cool something that's very small very, very quickly, and you can also rewarm it very, very quickly. And, the issue, whether it's the small system or the large system, is that life, whether it's an organ or a human or, anything in biology, is so much of it is water. 60% or so of our body is water. And once you have a transition from that liquid state to an icy state, that structure of the ice can be extremely damaging.
Yeah.
So then there's different strategies. You could either control it or you could even stop it. And I think that there's kind of two parts of the answer. One is that strategies that have been brought in have, to a large extent over the last 5 to 10 years, fundamentally changed what we can do on the rewarming side. And it actually is the case that it's an order of magnitude more important to warm fast than it is to cool fast. And if you're interested, I can go through the dynamic for that. But that is largely being solved now by basically bringing in a combination of some nanotechnology and electromagnetic frequency, where teams around the world are figuring out how to load the organ with these biocompatible nanoparticles and then have an external radio frequency field that creates a very homogeneous as well as rapid rewarming process. That's one thing that I think if you look at what was the number one breakthrough the last 5 to 10 years, that might be, that. Going forward, that no longer is the bottleneck. So now there are a lot of groups that are really thinking about, hey, we've only really used 10 chemicals to control ice historically, and there's such a large search space there. So we're starting to see, other tools from groups outside of cryology being brought in to what are the other molecules that would be ideal and what's the best way of putting them together. One of the groups led by Matt Powell thinks maybe we can even entirely create new liquids that cannot freeze. And then if you exchange the water with some of that liquid, it means that your biological construct can't freeze. Part of it is that we have a lot of these different platforms that are being brought in. But I think the other part is that the road mapping that we did also helped the cryologists see that you actually get a lot of the bang for the buck in transforming organ transplantation if you're able to slow down time without stopping it. So some of the first technologies that I think we'll see FDA approved, it's going to be taking a heart or a liver from only being preserved for hours, which is why we have helicopters, private jets, and all of these things today, to not having years or indefinite storage, but to have a week or, maybe 2 weeks or at least a handful of days. And that's enough to unlock a lot of the full potential on the benefit side, where you make it the global elective procedure and so on and so forth. So that part of it is actually interesting, that we probably could have done these high sub-zero temperatures that we call them, maybe about same type of temperature that you have in your freezer at home, where you don't get hours, you're now getting the days to a week or so. And it's just weird how the world works, right? That if we really decided we wanted to do that 2 decades ago, we probably could have actually solved the science for that.
This is a really nice segue into thinking about some of the technologies that are coming through. You've mentioned vitrification, and we should get there because there's been some really exciting stuff going on with that. And I think that's going to be really profound in terms of changing the entire equation in terms of how we can store human organs and beyond that, yeah? But maybe we could talk about, some of the technologies that we've had around for a few decades, like ex vivo machine perfusion. You've mentioned it, Seb, yeah? So essentially we have these machines where you perfuse your organ with oxygenated blood or some kind of blood substitute, and you can get preservation times up to 24 hours or maybe even more, yeah? And then there's this aspect that people have been playing around with. You can either do this at normothermic temperatures, like 37 degrees, or then you start to go down. Yeah? You start to slow the organ metabolism down. So you have these sub-normothermic systems, and then you have going all the way down to kind of hypothermic, kind of 4 to 12 degrees.
Yeah.
So maybe you could talk to us a little bit about why is that important? Why is it important to go from like a few hours to having days to understand, is this an organ that's going to be good enough to put into a person?
Yeah. So on the organ perfusion side, it can be something that gives you time. And that's where a lot of the historical benefit came from. And actually, my Chief Science Officer, Mike Taylor, he was the head of R&D for, what today is the world's market share leading platform. It's no longer necessarily the most advanced one, but it's still the one that's used the most, the life part of organ recovery systems. I think with the future of perfusion-based technologies when it comes to organs, one part is what you were connecting it to, that it really is valuable if you're able to evaluate which organ should be transplanted, or maybe even more, which organ should be transplanted in what context, and is this suitable for this specific recipient or not? You can go in and make transplantation much more of a precision-based science. And then the other component that we're starting to see more and more of is that since an organ is going to treat and cure a human being, you can actually envision that we should throw the same amount of resources that we do to treat a critical ill patient onto the organ. So the sky is the limit there. There's some examples of a little bit of maybe doing some gene therapy, but even things like taking, lungs that have pneumonia, curing them from pneumonia, and then you can transplant them into someone who's going to have a lot of immune suppression. ARPA-H has just funded a project by 34 Lives, where they're going to be basically taking kidneys that normally wouldn't be seen as transplantable and basically treat them, and then combine that with the assessment at the end so that you could transplant a lot of organs that otherwise would have been rejected. And then maybe the last thing where I think a big part of the future of perfusion is that it's not do you perfuse or do you use one of our biostasis platforms. It's more that they're extremely complementary, where the stasis is probably best for actually when you just want to buy the time, and also for transport, right? You don't have to have liquids circulating and things like that when you put it on the plane, or if we're going to do international exchange of these organs, the stasis becomes really good. But in order to know which organs should go into stasis, the perfusion plays a role. And then when you come out of it, the treatment part, the assessment, but then also that it actually becomes a fundamental part of the protocol. The first sub-zero demonstration of mammalian organs that were successfully transplanted in Nature Medicine, that did not work if you did not have the perfusion before and afterwards for the reconditioning and the preconditioning. So I think it's extremely exciting what that's going to be in the future, but it won't be enough. because once you go beyond 24 hours, you maybe can push it a bit more on the perfusion, but you are creating some injury to the organ. Whereas if it's in stasis, you basically have stopped time entirely and there's no continuation in the degradation.
One thing that to me is quite interesting always whenever we have these conversations in the podcast is to think a little bit about the regulatory strategy and the bringing these advances to the clinic. In this case, this is very different from the sort of things we normally think about developing a small molecule or a biologic or even gene therapy, right? In this case, you are working with an organ, adding chemicals and doing all kinds of manipulations. And then you have to show that this organ will be safe to transplant to somebody after being out of a body for a few days. So what is the regulatory strategy for this kind of development? Do you need to show in a clinical study that it's comparable to faster routes of transplantation? If there are chemicals involved, do you need to show that they're safe? What sort of conversations do you have with regulatory agencies so that they let you take these to patients?
There is a whole range of it, and I think that's a bit where my companies have started to get smarter on that specific question, and we're seeing some others out there too. The long-term dream here, right, is to do full-blown, let's take that organ down to cryogenic temperature, time is out of the equation, and now whether we want weeks or months or years, we have that. That, I think, will have a quite, not an extraordinary regulatory burden, but it probably will require, clinical trials with hundreds of patients, similar to what we've seen with some of these perfusion devices that Andy was talking about. Those have been hundreds of people in these clinical trials. One of the things that we're working on right now, together with some collaborators, is there a sweet spot where we can start getting out to, 5-6 times the current preservation durations without actually using any chemicals. So we still can go to these sub-zero temperatures. And the reason we can do that is if I asked you at what temperature does water boil, we will all know what that temperature is. But if I said, what happens at 160 degrees Fahrenheit? Not a lot of people would say that's when water boils. But it actually also is when water boils if you're at the top of Mount Everest. So some of these approaches are not using chemical ways, but we're perturbing the thermodynamic system in other ways. You could do it with pressure, or you can even do it with just having a constant volume where you constrain your system so it does not interact with the air or the atmosphere around it. So that type of approach, now you're talking more of a class 2 medical device where you can more compare it to other static storage solutions that are out there. So I think we'll see a range where it's going to be a little bit, let's take the step down into the paradigm of sub-zero temperatures first before we push it all the way down to the cryogenic. That's in the world of organs. And then my first company, I'm no longer part of it, but they're banking bone marrow from organ donors now. And that, it's just grandfathered in as a practice of medicine. So you actually did not need any more FDA approvals for it. It was more just showing all of the assays and that human bone marrow works really well to engraft in mice and so on. So you wanted to know all of the safety things. But they didn't have the hurdle of demonstrating that bone marrow transplants work. And same in transplantation. The hurdle is not to show that transplantation itself works. It's more, did you do anything to the organ that changed it too much? And some of the markers, with that collaborator, we saw that maybe some of the inflammatory markers are actually going in a positive direction compared to the standard of care, even if we're storing it for 6 times longer.
This is super interesting, Sab, because I've always thought about this in terms of different categories of cryopreservation, whether it's ex vivo perfusion, supercooling, or vitrification. Yeah, I kind of place everything in those 3 buckets. But I always think with biomedicine, time and time again, the things that really work in terms of translation often are things that are really simple. Like Boris Rubinsky at the University of California, Berkeley, his kind of idea of playing with pressure. So the temperature's going down, but you want to keep the volume exactly the same and you're increasing pressure. Yeah? So that... Correct me if I'm wrong. I mean, the way I've understood this is you're increasing pressure as you go down to these supercooled temperatures, and this prevents water molecules from essentially rearranging in space so that they can form the kind of lattices and crystalline structures of ice. That's the idea, and it's a truly that simplistic idea. And I love that paper he had in bioengineering where he laid this all out. It's a device, you put the organs in these plastic bags, and then you just increase the pressure as you go down in temperature.
Yeah.
It's like an incredibly elegant solution, in a way.
Yeah. And the latest generation of the family of those approaches is called isochoric because it's constant volume. Our collaborators have been seeing that you can achieve a lot of that even without letting the pressure build up. Just by being in the constant volume, you've added a kind of a third dimension because you were talking perfusion, supercooling, and vitrification. So that's kind of a temperature axis.
Right.
But we can add one more dimension, which is it constant volume or not?
Yeah.
And if you're in a constant volume, that itself is enough to decrease the probability of nucleation that you can get to sub-zero temperatures. And it looks like, extend preservation times by 6 times, maybe even potentially more, with no chemicals and no pressure.
So going back to JC's question, do you think that something like that is likely to be relatively easy in terms of regulatory oversight? Because the problem with everything else in supercooling is you've got the cryoprotectants, and then we always have this kind of issue when once you've thawed the organ's kind of in shock when it's back. And we're getting better with the cryoprotectants, but it seems like that toxicity issue still is quite challenging, yeah?
So I think yes to your first question, that the approach that doesn't use cryoprotectants is going to have an easier FDA pathway. On the cryoprotectant side, we're starting to see that renaissance in, what's the optimal starting components, and then also how do you combine them in the best possible way. And it should be this way, right? But then when you have these novel cocktails, even if it looks like they're going to play out to not be as toxic as the historical ones, they still are going to have a higher approval barrier because it still is novel.
Yeah.
So I think it should be that way. But my guess is that especially the amounts of cryoprotectants that you need. So, our scientific co-founders at Mass General presented this summer at the American Transplant Congress that they can go out to 10 days with human and pig livers and to 30 days with kidneys. It is true that they're using a small amount of cryoprotectants, but it's such a small amount of them that I don't think it's less that there's a question of it actually being a big biological or medical problem. It's more that the FDA just hasn't seen it before, so they still have to have the data of safety and so on.
Thinking about this as a product, what is the IP, right? For the cryoprotection, I get it, right? It's a compound that you use, and I can see that as traditional IP. For these other approaches that require playing with pressure and keeping steady volume, all of that is more like a process. That's almost like a trade secret. Or is there no IP? And if there's IP, why are you licensing to a potential user?
So there is quite a lot of IP in the field, also outside of the cocktail compositions, around the protocols. Some of the things actually end up being counterintuitive when you start thinking about these other thermodynamic paradigms. Having said that, I do think that a lot of the success here, it's about bringing the technology, but it's also bringing a vision for an entirely new way that the transplant ecosystem should operate. If you take hearts right now, a heart has to be transplanted within only about 20% of the US geography for it to be close enough between the recipient and the donor. If you start opening up a world where, that heart or that liver or whichever organ it is could come from anywhere in the US, and now you start adding in, it actually could be that it's a US liver that's going to Germany, and then it's a Swedish heart that comes back to California. I think a lot of the commercialization and what we're hearing from investors is that it's building that model. Because one thing that we didn't touch upon is in many times when they've done the top 10 medical breakthroughs ever, people put organ transplantation on that list. But it's because it's so conceptually powerful that you take someone who's near death, you replace a part of them, and then they're basically cured. But the numbers that we're talking about on the end-stage renal disease, 600,000 people in the US right now. Cardiac disease, also another 600,000. Hundreds of thousands on the lung side. then you have liver, you have pancreas, and so on. And if you combine all of the cases where transplantation could save a life, it actually is 1.5 times how many people you could save versus if you saved every single person that has cancer. So part of it is that there are a lot of times where you have an organ in one location where the specific transplant center that's close to that location would not use that organ. But there's another transplantation, if you just had more time and more geography, where they would do a successful transplant. And these numbers are quite crazy. There was a US government-funded report that suggested that 5 times more organs than currently were transplanted should be available from the current organ donor pool, right? So without more people saying that they would want to donate, if we just had the optimal logistics.
Why is that? Is it just that they're not fulfilling the criteria, or you can't find the right recipient from the donor, where the donor is in the time that you've got available?
There's a lot of pieces. Some you could solve, I think, without new technology if we really just had much better matching algorithms and things like that. Part of it is how the incentives work, where by and large, if I simplify, the transplant surgeon and the transplant center are held really, to a very high extent, they're held accountable for the 1-year survival, maybe the 5-year survival of the person that's transplanted, but not really held to the same extent accountable to what happens if I didn't transplant a patient and now they die when they're on the organ wait list. And you can see that example between different nations, right? Where, for instance, most of the developed world use a lot of relatively good organs from donors that, might be 70, 71, 72 years old. So if you look at Spain, they use about 25% of those organs. In the US, we only use about 4%. But that was just one example, right? Then you can see the opposite between Spain and the US, maybe when it comes to using a hepatitis C infected organ or, even an HIV infected organ to an HIV recipient. The bottom line is that if we took time out of the equation, now you never have to worry about that, okay, a certain transplant center is good at doing a certain type of transplant, but has to reject other types of organs, and that you have that mismatched, because once you start having days, that organ, you can basically go to every single transplant center in the world and say, do you want it or not? And sure, the closest ones on average are going to say no. Then you just send it a little bit further and you get that matching.
Is that because different countries have different criteria for validating which organs can go into which recipients, or is it due to the amount of time that you have to get the organ from the donor to the recipient?
Some of these, it's literally just the recipient and the donor are not in the close enough geography for today's technology. So that's part of it. But part of it is that you actually have a transplant center that might be close enough, and you have a patient that needs that type of organ transplant, but that specific transplant center hasn't specialized in the type of transplant that you would need to be able to successfully transplant that specific organ.
I think one of the things that will be interesting to see is once you're successful, if there are enough transplant surgeons that can do this, right? Because that's another problem. There's only so many people who know how to do this.
Yeah. So, JC, one of the things that often comes up is that it's interesting that becoming an organ transplant surgeon, in some ways, it's a really sexy thing, right? You're doing one of the most advanced surgeries and so on. But because of the lifestyle, fewer and fewer of domestic medical school students choose that versus other surgery, or maybe not even surgery. And a very high percentage of the US latest generation of transplant surgeons are actually imports from other countries.
Yeah.
But that's another example where our technology, once we end up changing the way you do transplants, instead of it being, okay, you're going to get that call Thanksgiving dinner that you have to go in and do a surgery, it becomes elective, where we can, both for the patient that also is on standby, in the middle of the holiday and might have to leave, it becomes an elective, no, we can wait until Monday or Tuesday morning and, just schedule it as if it was an elective surgery.
Yeah, that would be very interesting. I wonder how much have you seen in terms of cell type selectivity to resisting preservation, right? For example, in the heart, is there any difference between the atrium and the ventricle, or the pacemaker cells? Are they more sensitive to this? So I wonder if there's any data on cell type selectivity, or if there's any variability within an organ to susceptibility to preservation.
Yeah, so I think you see it within the organs and also between them. the heart is fundamentally more difficult to preserve than the liver, or especially the kidney, for instance. In the kidney, it turns out that the inner medulla is significantly more of a challenge to preserve successfully than the overall kidney. If you do the ovary, actually it's the opposite, that it's more difficult to protect the cortex, which is where all of the follicles and the egg reserve is, than it is to do the medulla. So it really depends on the given organ. Having said all of that, what is so powerful is that the technological platforms that are enabling you to control the main sub-problems, whether it's how do I control ice, how do I avoid toxicity from any chemicals I'm using. We haven't spoken about the ice cube effect, right? If you put an ice cube in your drink in the summer, it cracks. How do we avoid that? Those problems are kind of universal. So as we are getting better and better at solving those problems, the solutions, at least at the platform level, also are quite universal. So the ability to do horizontal translation is quite large, but it's not the one-for-one. You still have to customize the preservation protocol for each organ system.
This is a nice segue also into thinking about this more broadly, yeah? One part of this is that by moving these technologies forward, you can make a lot more organs available for clinical transplantations. But then there's always going to be loads of human organs that are never going to be an organ that you would want to be transplanted into a recipient. However, it's like an incredible resource. And the research community really hasn't thought about how to leverage whole organs in terms of if we could solve the problem of being able to preserve and store organ tissues in just slices, that could start to create a kind of new type of system that retains all of the structures that are present in a living human being. It seems like it could be an incredibly useful resource to forward translational research.
This is one of those examples, right, of how starting to develop the tools for organ transplantation just opened up this realm of what might end up being, if we're successful with, the vision around how we can accelerate research, might end up in the long run saving 10 times more people than we can do on the organ transplant side, because we could touch virtually any disease that we don't have a treatment for now. We could provide a tool that accelerates it. So maybe taking a step back, if you think about most of our current treatments and medicines were developed either in cell models or in mice models. And then it's only when you start getting into phase 1 clinical trial that you expose human biology. And it's not until phase 3 trial that you're exposing it to the variety of human biology across ethnicities and ages and so on. So what if we could flip that order, that at the very beginning, alongside cell models and mice, we have an entire pillar of human biology that you can do your early studies in. Think about, where do we have the biggest set of failures in medicine? Well, it's for all of the neurodegenerative, the psychiatric, any type of disease that has to do with the brain, because the mouse or even a pig doesn't represent a human brain, but the human brain tissue actually would. And there's been vast strides in being able to culture, so you can study human brain tissue now for many weeks in culture. The tools of how you can interrogate it, whether it's the omics revolution or the imaging revolution and all of the molecular assays. Maybe when we look back on this, 10, 20 years, that unleashing these technologies to enable an ecosystem where you basically create rich living libraries of these tissues of the different organs, the researcher can order, okay, I would want Alzheimer brain tissue. Someone else says, I would want this specific type of heart disease, heart tissue, and so on. In some ways, the US identified this, right, with everything that went into organoids, organ on a chip, and so on. Like, many billions has gone into developing those platforms. But at the end of the day, even if you did it perfectly, that you recreated the tissue, you're going to be recreated something that is similar to a healthy tissue. You're not going to have captured the real disease. Because if it's cardiovascular disease or Parkinson or something, it takes decades for that phenotype of the disease to develop in the live human organism. And we can represent that if we're collecting the tissues from, people the minute after they're dead. You have living tissue from every type of disease, every age, all ethnicities, both genders, and so on.
I suspect bioethicists will have some interesting things to say about cryopreservation of human brains. I suspect they won't be completely on board with that.
So I think there's many aspects of ethics, right? Is the donor aware of what they're donating? Is there a proper consent? All of those things. And that actually, especially in the US, the organ procurement organizations have developed quite good protocols for that, but there's probably still room for improvement there. I think, personally, I would not want to be involved in, hey, we're going to restart an entire human brain, have it be conscious. That would be quite crazy. The vision I was talking about is where it's these really small representations of the organs, a precision cut slice. It's only 300 microns or so thick. And this is actually done sometimes when maybe there's a surgical need to do brain surgery where they take out the piece of brain tissue. So for instance, in epilepsy or, maybe in a tumor. And the people who know much more about me have kind of concluded that those small tissues, while you can see function and these different metabolic processes and so on, in that sense, really valuable learning tools, it's not that that's recreating consciousness. I think there's a lot that the different communities and the ethicists, the bioethicists need to be involved with, but that's something that's been done for decades. So I wasn't really proposing a new way of using brain tissue, more making it available in a democratized way, because there's so many labs that would want to use more of it than they're able to get their hands on.
The question for me about this is, how do you go about it? Are you thinking about this in terms of one of your companies where the company has its research arm that's trying to move forward the cryopreservation approach, and then on the side there's a biosample research customer revenue stream that comes through also providing non-transplantation ready tissue, which is just for research use only? Or is it a non-profit?
We've been thinking about it from a public benefit corporation perspective and have also had conversations with a lot of the non-profit research institutions. So it's at this point mostly thinking about it from how do we provide the technology that would enable the logistics. And I think all of those considerations that you were listing out need to be taken into account to scale something. There's also this tension, right, where sometimes in order to make something big enough from a scale perspective, you want to have that there's at least some profit margin in there so that you can entice the investors. In the US, we kind of have two systems in parallel, right? If you're getting a piece of cartilage transplanted into your knee, that might come from a for-profit company. And if you're getting the heart transplant, that's coming from a non-profit.
Right.
So both of the models seem to be delivering patient value. It's too early. Right now, the number one goal is let's get the first things approved for organ transplantation. Then we'll see how we go from there.
Yeah. I mean, one way you could view this is in the UK, they have the UK Biobank, yeah? I mean, the UK Biobank's kind of looking at this from a slightly different angle in terms of just deep phenotyping and genotyping of the UK population, like a big slice of it. And of course, that could be part of a biobank here, but this also is more a kind of source of biospecimens. The value here is in the biospecimen, because the biospecimen is basically a slice of somebody who has the disease, which would make drug assays and all of the things that you could do with that tissue much more productive, it seems to me.
Yeah, and being actually from an organ donor family, my father-in-law was in a traffic accident and then donated. Having seen it from that perspective, and then also I'm on one of the boards, so one of the high-performing organ procurement organizations in the US, there is a huge value often to the donor family to know that, okay, in that most tragic event that maybe they've ever gone through, there's also contribution to an organ transplant, or maybe contribution to a cure for a certain neurodegenerative disease that there's a family history of, and so on. It should, of course, only be voluntary, right? Who donates into these types of living libraries in the same way that it is for organ transplantation. But it seems that historically, across many countries, you've seen how it's not just the end output from that organ or that tissue, but the act of donating it has a big meaning and value also for the family that's in this really tragic moment.
Absolutely.
So you were talking about the ice cube effect of putting it in your drink and cooling it. So that's a perfect segue into the traditional question we ask all our guests. What is your go-to drink after you get your paper published in a high-profile journal, or a new investor gave you money? What is your go-to drink to celebrate?
Yeah. One answer is boring, that, I would put in a really good workout and, drink water is my favorite.
Yeah, that's very boring. I agree.
But when I do arrange parties, something since I was relatively young, one of my favorites is the opposite of ice cube. So different drinks that you can actually light on fire. Sambuca is one of those that's quite good. And I even have this party trick where not only do you have the shot on fire when you drink it, but if you learn how to basically spurt it out in the right way, you can do fire breathing with it.
That's very nice. Andy, are you game to try that? I certainly have a couple of shots that I also set on fire.
Always happy. Maybe we could try our fire-breathing wives, JC, to do it with us.
I'm sure that they're going to love it. Seb, it's been great having you on the podcast. It's been a great conversation, and I really thank you for your participation.
Yeah, it's just such an exciting area, Seb. Really looking forward to seeing how you continue to take this forward. I mean, there just seems so many opportunities. In fact, that's perhaps the biggest issue. What do you concentrate on in the near term? Thank you so much for sharing your insights. It was a real pleasure.
Well, Andy, I hope you enjoyed this conversation as much as I did. I thought it was a very informative conversation about an area where there is a clear unmet need. And to me, what's very interesting is that the solution is right there. There are different ways in which this community is making progress. And clearly, there's already some wins in this space. So to me, the question becomes, how do you turn this into a successful biotech business? Because the need is there, the solution is there, but I get the feeling that there's not enough capital coming into this space. It would be interesting to see a business plan to understand exactly where the return on investment might be, so that investors are more informed about this area, because clearly there's some low-hanging fruit that is ready for collection, I feel. So to me, that is one of the things that I would like to learn more about, but I don't know what you think.
Yeah, I find it really interesting that this is an area where there's still comparatively little funding compared with some other areas of science funding. And he's taken, a decade to put the Biostasis Research Institute together, and it has a few $100 million of funding, and that's no small potatoes, of course, and credit to the Organ Preservation Alliance and Seb, but you just wonder, considering the benefits that could accrue to patients from some of these efforts for keeping organs alive and finding ways of getting more borderline organs into transplant recipients, it seems like funding here could make a big difference to patient lives. I really don't get why more money isn't going in. But I think you've touched upon the problem here, which is what are the business models, what's the market, the solutions of keeping organisms alive, meaning that you can then expand out the number of organs that you can transplant into people is quite compelling. You can find better HLA-matched recipients. You may be able to have other advantages like reducing the need for long-term suppression all of these things are going to make a difference, yeah? But at the end of the day, the question is economics and how do you make this work? In the machine perfusion space, there are companies, I think Seb mentioned Transmedics as, a company that's developed portable perfusion and monitoring devices for donor organs. And there are others, but, it's mostly these device providers. And so the question is, how do you think about the economics of this, yeah?
Yeah, I think we would have to think about this with more granularity, right? Because one thing is these perfusion machines that are more like a device that you would sell to tertiary care centers, presumably. So that's one model and that's one market. And then what's coming behind that, the cryobiological approaches, that's a different market and a different model, presumably, that we would need to understand. And then the vitrification that we didn't really talk too much about, but that's yet another market that has its own challenges, because in that case, you really need to deal with a much more stringent regulatory landscape, presumably. So all of these different approaches will have different markets and different economic rationales. So it's very interesting, and I'm glad we had Seb here. I was also glad to welcome him because his choice of cocktail was quite interesting. It's not really a cocktail, right? It's a shot that you said alight.
It's fun. It's fun.
Yeah, we can do that.
So what are the factors that you need to take into account when
playing with fire?
Yes.
I would say that, people shouldn't go and try to set their margarita or their Negroni on fire tonight. Don't try that. Normally, for these kind of drinks, what you need is very high-proof liqueurs. Right? For example, one shot that I make that I flame is the Flaming B52 that has 3 different liqueurs. So you form 3 different layers. And then at the very top, you float a little bit of rum that is about 110 proof. So that's very flammable. And that's what you flame. That's where you start the fire. And so only the surface of the shot is what gets alight. So if you want to flame any drink, you need to provide this very high proof liqueur to get the fire rolling. That's number one. And number two, some people try to start the fires with matches, and that's not cool. Matches, they have sulfur, phosphorus, things that you don't want anywhere near your drinks. So what you need to do is to use a butane lighter, turn it on, and just use the flame, right? Or one of these torch that you use for pastries or for creme caramel and that sort of thing. So that's the kind of fire that you need for a cocktail. So if you do that, you will not alter the taste of the drink. But at the end of the day, Andy, I don't want you to experience second-degree burns if you go down the route of playing with this.
Yeah.
Safety first.
Anyway, this was a really interesting conversation with Seb. We'd like to thank him for coming on the show. We'll provide some details in the description below about different sambucas and some ways to prepare to light them and other materials associated with the drink. So thanks very much, everybody, for listening, and see you next time. Cheers, Stacey.
Cheers, Andy. See you next time.
Vivo, 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 vivo,